Hello everyone. So today we're going to take a look at the first part of how we would add and subtract vectors. I'm going to take lesson 7-2 from our website and I'm going to break it into 2 days, especially as we head into the long weekend here. So we'll do the first part today and then we'll do the second part after the long weekend. So as we start looking at adding and subtracting vectors, the first thing that I want to just briefly look at is the idea that our algebraic operations apply here as we work with vectors. So the same way we can expand brackets, use our distributive property, collect like terms, the same thing would apply here. So I could actually take this expression here and distribute the 5. So we would have 10 times vector x plus 15 times vector y minus 2 times vector x plus 4 times vector y. We could then collect our like terms. So if we do that, we would end up here with 8 times vector x, and we would have plus 19 times vector y. But the real question then is, what does this actually mean? If I'm taking 8 of vector x and I'm adding on 19 of vector y, what would that physically look like? And there's two interpretations or two rules that we use to talk about this. Both of them are based really on this first rule that we're going to call our triangle law. So remember, in our first lesson, we defined a vector to be a directed line segment. So in the past, we've had line segments. So if I take away the arrow, we might have a line segment AB, and we could use that to represent a number of things, and that might have a measurement, some sort of distance or length between those 2 points A and B. Really what a vector is doing is saying we still have that length or the distance between A and B, but it's now also attaching a direction to that. That specifically we are moving from point A to point B, that the direction part is what is now making this a vector. And if I want to add two vectors together, say I want to add AB and BP, so I have now given a physical representation of that. I have a vector that goes from A to B and a vector that goes from B to P. Really what we're doing is we're just following the path that these vectors are creating. So if this is my start point here, and my first vector says I'm going from A to B, and then my second vector says starting at B, go to P, my result, or the answer to this addition, is actually this vector then that starts at our start point and goes to the end point, P, and this then we would call our resultant. So the result of adding these together is really just this path that is created as long as the vectors are pointing in the right direction. So this vector with this direction is saying to go from A to B. This vector is saying to go from B to P. So if we follow that path, we end up starting at A and following the arrows of these vectors, we end up at P. In other words, our resultant is this vector then AP. And we can see that in the diagram, that this is resulting in this vector AP. So really here, what we're doing, informally, we could say, then follow the path created by the vectors. More formally, in the box here is how we would word this. We'd say when vectors are joined from the head of the first, remember that the head is the arrow, so from the head of the first to the tail of the second, the tail is the starting point. So when I have vectors that are joined in this way, the resultant is from the tail of the first, our starting point, follow the path, and we'll end up at the head of the second, and there is our resulting vector. So now we can actually extend this then to not just two vectors, but we could extend this to 3 or 4 or more vectors. And really what we're looking for is I don't necessarily need this diagram. I'm just looking for this path that is being created. This path that goes from A to B, which is what my first vector is saying, and then from B to P, which is what my second vector is saying. And notice that as we join these two, that we end up with these points being the same here, and we end up with this result that takes us from A to P. So I'm doing the same thing here. I'm just looking for what path am I going to follow. So if I assume that I am going to start at A, my first vector says go from A to B. So now I'm looking for, well, if I'm at B, what is my next direction? And my next direction here with that overlap then says, well, starting at B, we're going to go to D. So now I'm sitting at D, and where do I go? So I'm now looking for my vector that will match up here, and here it is. I'm going from D to K. And now I'm sitting at K, and if I reorder this, then I'm going from K to L. And if I follow this path, it's saying go from A to B, then go from B to D. When I'm at D, go from D to K, and from K, go to L. In other words, if I start at A and I follow this path, I will end at L. So the resulting vector, then adding these, is the vector from A to L. Second one looks a little bit trickier because there is this subtraction here. Don't forget, though, that we can change this into addition by saying that we are adding the negative of vector AC. And we are adding the negative of vector RB. And then we will add on RT. And from our lesson last day, what we will see here then is that if I have the negative of a vector, remember this is just saying it's pointing in the opposite direction, so the negative of AC is the same as vector CA. And the negative of RB is the same as vector BR. And then we have our RT still on the end. If I try and start this path, it looks like I go from T to C, and then from C I'm going to A, and then as I search I kind of get lost because there's no more A's here. So that's fine, I'm going to leave that like that for now. I'm going to say I'm going from T to A, if I join just these two. And I'm going to look at these two here, and I can see these two form a path as well. I'm going from B to R, and then I'm going from R to T. So I'm going from B to T. And if we look here, hopefully we realize the reason that we got stuck is because T is not actually my starting point. Actually, B is my starting point. This vector goes from B to T, and then I can join that here by saying I'm going from T to A. So if we want, we can reorder that. We can say B to T plus T to A, and that will then result in our final vector, our resultant, which is saying we're going from B to A. And if you wanted, you could try and create a sketch for this that looks something like this, but instead of having only 2 vectors, we would actually have now 4 vectors with some sort of path taking us from the beginning to the end of that path. We can also now extend this in a slightly different example to something that is in 3 dimensions. So in this diagram, I'm going to define this in this way. In our first lesson, remember that this little caret on top referred to a unit vector, means that this is just a vector that is 1 unit long. So I have these 3 unit vectors, I, j, and k, and they have the same direction as AB, AC, and AD respectively. So I'm just going to pause there for a second. This is saying that vector I and AB are the same thing. So there is our vector I. Vector j is the same as AC. So here is our vector j. And vector k is the same as AD. So there is my vector k. And we have this rectangular, actually correct that, I'm going to make this a cube so that all edges are the same length. So not rectangular, but a cubic prism that is given. Express each of the following vectors then, so here's these 3 vectors, in terms of I, j, and k. So this is kind of working backwards. It's now like I'm giving you the final result, and I want to figure out, well, what vectors would I add together to get some certain result? So my first one is I'm trying to represent this vector here, GC. So if I want GC, what I have to realize here then is that GC, if I want to try and relate this to I, j, and k, is the exact same as BA. They are parallel and they have the exact same length, so GC and BA are the exact same vector. Now, this is pointing in the opposite direction to I, so I'm going to flip its direction. Remember, to do that, what I can do is just make this negative. So I can say BA is the same as the negative of AB. It is the opposite direction to AB. And now we have this, AB is the same as I, so GC then would be the same as the negative of vector I. If we look at the second example, BH is a little bit more complicated because now we have the diagonal of this front face. So we need to figure out, well, how are we going to now represent that using these three vectors I, J, and K? First thing we need to realize is that I, J, and K are talking about edges, and BH is not an edge that is going across the diagonal of that face. So what I first want to do is pick a couple of vectors that will represent BH, but using edge lengths. So if I do that, assuming this is my resultant, what I can say is going from B to H is the exact same thing as going from B to G and then going from G to H. So it's the opposite of what we are doing here. And now I'm trying to look at, well, in this diagram, I want to get to I, J, and K. So what are these equivalent to? So B to G is the exact same thing as A to C. And G to H is the exact same thing as A to D. So these vectors then are the same. And once we have that, then we can see, well, AC is really just J, and AD is really just K, the way that we have defined this. Now, in this example, once you get going and doing this regularly, I'd say this is sort of an extra step. I don't necessarily need this one. I could look at the diagram and say, well, BG is J, and I can say that GH here is really just K, and I don't necessarily need that in-between step. But as we're initially looking at this, that's maybe a helper step to understand what's happening in this diagram. Last one, if we look at CF, okay, this one we call a body diagonal, okay, as we take a diagonal that goes straight through the cube. So now I'm looking for a path that will get me from C to F that uses edges only, again, so we can do what we did here, relating it to the edges of this cube. There's a number of paths that we could do, but we are now in 3 dimensions. So to get from C to F, I could go from C to G, G to H, and H to F. That would get me from C to F. Likewise, I could go from C to E, from E to D, and D to F. Or I could go from C to E, E to H, and H to F. So there's a number of different paths that we could take. I've only just listed out a couple here. So I'm just going to pick one. I'm going to say, well, let's go from C to E. And I'm going to say, let's go from E to H. And I'm going to go from H to F. And that takes me, if I follow this path, even in 3 dimensions, gets me from C to F, the original vector that we were looking at. And this time I'm going to leave out that middle line. I'm going to say, okay, if I want to go from C to E is the same as this vector here, so that is the same as vector K. E to H is parallel, same length as this vector here, AB, so EH is the same as vector I. Lastly, if I want to go from H to F, that is this vector here. And again, we need to be careful. Direction is important. So it is the same, but opposite direction to J. So if I want the opposite direction, then I would have to subtract that off, so I go in the opposite direction. So CF then would be K plus I minus vector J. Similar idea, just a different shape. Okay, this time I've defined some vectors in this array of triangles, and we're going to do the same thing. How can I write vector x? So there is my vector x here on this edge right here. How do I write that vector x as a sum or difference of, and in just some different ways, 2 vectors, 3 vectors, 4 vectors. So again, keep in mind that as we do this, as we add vectors, there is my start, there is my end. I am looking for a path that will take me from the start to the end that is going to use these number of vectors. Initially, I'm not concerned about direction. I'm just looking for a path, and then I will look at whether I have to add or subtract that vector to get the right direction. So if I'm only allowed to use 2 vectors, essentially I'm allowed to use 2 edges. So I'm going to say, well, I could come across here and up here. That would take me from the start to the end using 2 vectors. So x would then be equivalent to, if I follow vector A, and I want A in the direction that it is pointing, and then I would have to come across here, but notice that this is in the opposite direction to E. So if I want to be in the opposite direction to E, then I'm just going to subtract that off. Okay. The idea here is that that would be the same as if I was adding the negative of vector e. Okay, so that's the idea that we're using. If I take a and I add on negative e, that would form this x, or we can simplify it to this right away. If I use 3 vectors, I'm looking for 3 edges to get me from the start to the end. So I could say 1 edge, 2 edge, 3 edge gets me to the end. So vector x equals, I have vector a. And if you want to see that negative idea, I have vector a. I want to go this way, so I want to add on the negative of vector d. And then I want to go this way, which would be then plus vector f, which means vector x is then equal to a minus vector d plus vector f. Lastly, I'm going to look at this as 4 vectors. 4 vectors, there's a couple different ways. I could do 1, 2, 3, 4. 1, 2, 3, 4. So we have a couple different paths that we could take. I'm going to take this path where I'm going to go here, 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 and here. I'm going to leave that in between step out this time. I'm going to say I have vector A. I want to go this way, which is adding negative d. So I'm going to say subtract d. I want to go this way, which is adding negative g. So I'm going to subtract vector g. And then lastly, I want to go this way, so I'm adding negative h. So I'm subtracting vector h. And that gets us then, if we follow this path, all the way from the start to the end of vector x. So in our last example, we were using the idea of point-to-point vectors, and here we're just using the labels that we have put on the vectors and then interpreting whether we need to add or add the negative, which turns into a subtraction of vectors. Hope that helps. Okay, there's an assignment there for you to look at to practice some of these things. Have a good long weekend, and we'll pick up with the remainder of this lesson then on Tuesday after the long weekend.